I place an object at a certain height, and then I let go. The object falls downward. Gravity is pulling it downward, right? Okay, now the object falls downward naturally. I do not apply any forces on the object. So the natural motion of the object is downward, right? Now, when object falls down, what happened to the gravitational potential energy? Decreases, right? So gravitational potential energy is proportional to altitude, height. So if it's falling down, then it decreases. So we can say that whenever object move in its natural motion, the gravitational potential energy decreases. Okay, so where does the gravitational potential energy go? It goes to the kinetic, right? So as it falls, it gains speed, fall faster and faster. Okay, now consider the opposite. Let's say now I take the object from the ground, I lift it up. I lift it up. To do that, I'm going to do a certain work. I'm going to need to expend my energy. I need to make effort to lift it up. So I'm using my energy. And then since I'm going against the natural motion of the object, so natural motion is downward, right? So I lift it up, I'm going against the natural motion. So whenever I go against the natural motion, work need to be done, okay, by an external force. So I'm applying the force, and then the object gain potential energy. Okay, so simple idea. You have learned about it in your high school. So now, whenever object move against its natural motion, remember the potential energy increases. Okay, now when the object is high up there, the potential energy is higher than at below, right? So now the object has potential energy, it gains back the potential energy, and the moment I let go again, and it falls back down again. So why should it fall down? Maybe you say, okay, it's gravity, but we are looking from the energy perspective. Why should it fall down? Is because now it has gained back the same potential energy, and since it has energy, so it tends to do work. Just like when you wake up in the morning, if you feel very excited, then you're more likely to take action, to do work the entire day, right? So if you wake up, you feel very tired, you feel very sian, right? So there's no action, there's no work to be done. So whenever an object has potential energy stored in it, then it tends to do work. So that is why I lift it and it falls back down. Okay, two things to take note here. First, I can say that when it moves against natural motion, when I move an object against its natural motion, the PE increases. And if I move with the natural motion, okay, I do not touch it, the object moves by itself in its natural motion in the field, in the gravitational field, then the PE will decrease. Now, for all the examples, the gravitational field has to exist, okay? It has to be there, because without gravitational field, there's no gravitational potential energy. So in all the examples, we will assume that the object, they are all placed inside gravitational field. So there must be gravitational interaction to have potential energy. Okay. Now, so what we understand about gravitational potential energy, just to put it simply, is that it is a stored energy in a body. Okay. So a body needs to be there to acquire this potential energy. If there was no body, right, then there's no energy. There has to be a body placed inside the field to acquire the potential energy. Okay, if no body, then nothing. Okay, now here we look at what are the things that affect the gravitational potential energy. So you have learned about GPE equals to mgh, right? Now here's a question. We know that the higher the object is placed, the higher the gravitational potential energy. Is it often the case? Is there any exception? You see, here I got 2 kg object placed 1 meter above ground. If I calculate E equals to mgh, 2 times 10 times 1, 20 joule. I can also have a 1 kg object placed at 2 meters from the ground, which is higher up, right? Higher up, higher than this one. But if I calculate mgh, also I get 2 times, it is 1 kg times 10 times 2, also 20 joule. So this tells us that gravitational potential energy does not only depend on height, it also depends on mass. Very important, it is depend on mass. Okay, you can see here higher, but they have the same gravitational potential energy. So GPE is not just location dependent, it is also mass dependent. Now, for the same height, let's say we take the same height from the ground, h. For the same height, if I place 1 kg object, it is going to gain certain potential energy, EP1. And if I increase the mass at the same height, I place a different mass, which is heavier, okay, heavier. So let's say 5 kg. Then the potential energy, of course, is going to be higher than the first one. So the more the mass placed at the same height, the greater the potential energy. So at the same height, all the potential energy is different because the mass is affecting it. Now, we want to make everybody the same. We want to make everybody the same. So I would use another quantity that is independent of the mass of the object. That is only dependent on the location. So I would take GPE and then I divide it by the mass. That is GPE per unit mass. Okay, if you look at the unit for this, is J/kg. How much gravitational potential energy does an object gain if I just put everybody be 1 kg? Okay, because I don't want the mass to affect it. I just make everybody is per 1 kg so that I eliminate the depend on the mass. Okay, so in other words, I can say that if I make per kg, then I can find the GPE at specific height regardless of the mass. Okay, regardless of the mass, because everybody is just 1 kg, 1 kg, 1 kg. So this makes this quantity become location dependent. Location dependent only. The mass doesn't, no matter what is your mass, okay, doesn't affect it. This doesn't affect my quantity. It's just joule per kg. So if you, no matter what mass you want to put in, okay, you would put at the same height, okay, you can calculate the gravitational potential energy that it will gain. All right. So this quantity, the GPE per unit mass, is gravitational potential. Okay, gravitational potential. Now let me explain. Gravitational potential tells you how much gravitational potential energy gain independent of mass per unit mass. So example, if I have 3 points, let's say point A, point B, and point C, here is 100 joule per kg. Here is 50 joule per kg. And here is 25 joule per kg. All this shows the gravitational potential at a specific points. Okay. Now we know that the higher is the object placed, the higher will be the gravitational potential energy, right? So the higher the location, the higher will be the gravitational potential. What is it? What is it really gravitational potential? So it is just information, just information. What do I mean by that? Let's say you want the object, you place the object of 1 kg, you place it at point A. You place it at point A, then the object is going to gain how much potential energy? You can calculate. So 100 joule per kg. So the object is going to gain 100 joule of potential energy. If you place the object at, let's say, point B, then the object is going to gain 50 joule per every kg. So if it's 1 kg, it's just 50 joule. If you place 5 kg, then 50 times 5, 250 joule of gravitational potential energy. What is the difference between gravitational potential and gravitational potential energy? Potential means that it lets you know ahead of time what you are going to expect to get ahead of time. For example, 100 joule per kg, you know that when you put the object there, it's going to gain 100 joule of energy per every kg it has. So it is information. If you do not place anything at that point, will the object gain potential energy? Nothing. There's no body there, so there's no gravitational potential energy. Remember, gravitational potential energy is stored in a body. If there's no body, if you do not place anything at that point, then nothing happened. There's no outcome. It remains as just a location, and it only tells you information, okay, how much you're going to gain here. Okay, so that is the difference between gravitational potential and gravitational potential energy. You can think of it like, let's say somebody come and they tell you, I think that, okay, that specific location is it has a very good potential for a restaurant business. Okay, so if you do not go and open the restaurant, will you get the customers? You do not get customers, right? So you have to open the restaurant at that location to get the business, to get the customers. Now, mind the words, location. These people, he tells you, he said, that location has a very high potential. But if you do not open the restaurant, you do not get any outcome, right? Same concept as gravitational. I say that this point up here has a potential of 50 joule per kg. If you do not put object at this point, there's no outcome. Nobody gained the potential energy. Okay? Nobody gained the potential energy. So the word potential here, it means what? Without action, there's no outcome. Potential just means without action, there's no outcome. Okay? So, and also you can think of it like, let me give you another example. You can think of it like, for example, like a spring. Okay, let's say I put a spring here, horizontal, and then I compress the object. I place object in front. I compress the spring up to this point. And then I launched it. I released, and I measure how far it launched the object. Okay, let's say I got 20 cm. I write down here, the first marker is going to give me 20 cm. Now I repeat the experiment again. I start again, I put the same object, the same mass. Now I compress it further back to this point here. And then I launched it. I measure again how far it reached. This time it reached further, 40 cm. I keep doing that on different location, 20, 40, and 60. What are all these marking? Now I remove my object. Okay, I remove my object. I only have the marking on the spring. What are all these marking? They are just information. They tell you if you compress to this marker, you are going to get the object to reach 20 cm. If you compress to 40 cm, then you're going to get the object reach 40 cm. Okay, so if you place the object, if you place the body there, then the body will gain the energy. If you do not place the body there, then it just remains information at a location. And that is the whole idea of gravitational potential. It is a location base. Okay, so it's pure information. Now, I hope that makes sense. Okay, so so far, what we have understood here, you see, the natural motion of object downward, if I put it in a gravitational field, it will fall down. Okay, so high object fall from, let's say, point A to point B. Here, I would say this is a point of high potential. Potential increase with height, okay? And this is a point of lower potential, low potential. So if the natural motion is downward, that means as it falls down, the object loses potential energy, okay? So I can say that, I can conclude that the natural motion of body is from high potential to low potential, always, and it applies everywhere. Okay, let me give you examples. It applies in electricity as well, in charges. The natural motion of every body placed in the field is from high potential to low potential. So it's like a charge, similar to charge. If you have a positive charge and a negative charge, a charge is very similar to masses, right? Mass has field, charge has electric field, okay, also field force, same as magnetic. Magnetic material also has magnetic field. They are all field forces. So if you place the negative in the field force, in the field of this positive charge, then what happens? It will be attracted towards it, right? This is the natural motion, right? If you just let it do whatever it wants to do, where will it go? It will move towards the positive. I don't touch it, right? So it will move towards the positive naturally. That is the natural motion. So looking at this motion, then I know that this point is high potential and this point is low potential. Okay, because object always move from high potential to low potential naturally. Now, if I reverse the charge, positive and positive, I put a positive here. What is the motion? If I don't just let it be, it will repel, right? It will repel. So the natural motion would be like this. That means where is high potential point? This is high potential point, and this is low potential point. And as it moves, what happened to the potential energy? The potential energy decreases. Whenever it moves from high to low, potential energy decreases. Same as in an electric circuit. In an electric circuit, you get a flow of current, okay? You get the battery, okay, let's say we have this negative, positive. Current flow, conventional current flow follows the flow of positive charge. So we have positive charge placed here. This wire connecting the positive and negative plate. So it creates a path for the electric field to act. So if I put a positive charge here, it will repel it and move in this direction, like this. This is the natural motion of the charge, of the current, right? So here we can say that where is the high potential? The positive plate, right? Because it's moving from positive to negative. So we know that this is high potential and this is low potential. And as the charge moves, what happened to the potential energy? Same here, all the same, potential energy decreases, right? So when the charge moves around the circuit, their potential energy decrease. And since there's a decrease in potential energy, there has to be some increase in other energy. What are the other energies? It could be like light, if you attach a light bulb. Okay, so the potential energy drops and convert to light energy here, or heat energy. Okay, so when the charge arrives at the negative plate, what happened? This charge got no more energy left, okay? Got zero potential. So what happened inside the battery? Let me zoom in a bit. This is your negative, this is your positive. Inside the battery, our same charge, our positive charge starts here, right? This is the internal circuit already. Just now we were talking about the external, right? The charge move in the circuit outside, and this is inside the battery. What happened when you push the charge towards the positive plate? You see, what is the natural motion? Positive should be repelled by positive, right? So natural motion should be to the left. You push the charge to the right, that means you're going against natural motion. What happened? Point number one, move against natural motion, PE increase. So when the battery brings the charge from the left side to the right side, it is moving against the natural motion. So it increases the potential energy of the charge. Okay, so it increases, so sacrificing its own chemical energy, the chemical reaction in the battery, convert to potential energy, give the charge, and then the whole process repeat. When the charge arrives at the positive, again, it moves around the circuit, losing the potential energy. Right? So that is the concept behind, just to give you a little bit idea, okay, of the difference between the potential and the potential energy. They are completely different. Very simple. There's a, sometimes it's quite confusing, okay, but there is a subtle difference between them, right? And for gravitational field, for electric field, they all follow the same concept. Okay, so the bottom line here, what are the key points that we know is that potential energy, whenever we move in natural motion, potential energy decrease. And whenever I move it against natural motion, I'm increasing the potential energy. So I increase the stored energy. And please remember this, we will apply to the next part. Okay. Okay, let me erase this and I will go to the next slide. In the next slide, we will look at the gravitational potential energy and the relation between the Newton's law of gravitation. Gravitational potential energy and Newton's law. All right. Suppose that there is a mass placed on the ground, M, and I lift it up. So I do work on the mass, it gains potential energy. Okay, so here I can calculate PE equals to mgh. The h over here from the ground, right? We take the ground as our reference point. Now let me ask you, what is the potential energy at the ground over here? PE, 0, right? 0. Because there's no height, the height is 0. So is it really 0? Now, here's the question. Let's say I dig a hole like this, and then I place the object over here. What happened to the object? Falls down, right? Falls down. How come it falls down if the potential energy is 0? Because if the potential energy was 0, object would not move. It would not have the energy to move. But if I dig a hole here, it still drop, right? Still drop. Means that it still possesses some amount of potential energy, right? That also means the potential energy at ground level is not 0. Because if it was 0, it would not fall. It would just stay float like this. Since it falls down, that means it still possesses gravitational potential energy at the ground level. But why do we call it 0? Okay, now, where is the real 0 point? Where is the real 0 potential energy? Now, if you just keep digging this hole until the center of the earth, if you let it fall to the center of the earth and it stops, that means at the center of the earth is where potential energy is 0. Okay, so as long as it is at a distance from the center of the earth, the object have potential energy. Okay, so the true zero point is at the center of the Earth. That is the first one. We actually got two. Another 0 point, where is it? Another 0 point is at very far away, okay, until like it's outside, almost outside the gravitational field of the planet. Because if you are outside the gravitational field, there's no force attract, there's no gravitational interaction, so gravitational energy will be zero. Okay, so one is at the center of the planet, another one is at infinity, we say. Okay, the point is very, very far away that we just call it infinity. So we say here 2 points where PE is equals to 0. First is at infinity, and second is at center of the Earth. But why do we take the ground as 0? Okay, here's the answer. We take the ground as 0 is because all we are interested about is just the relative value or the comparison from the ground. We're only interested in knowing how much is the potential energy compared to our reference point, compared to our ground. Let me explain. You see, here, 2 kg object placed above ground. Okay, if I calculate the gravitational potential energy, P mgh, 2 times 10 times 1, 20 joule. Here, I will say that the potential energy of the object is 20 joule more than the ground. 20 joule more than the reference level, which is the ground. Okay, where's my reference? My reference, I set it at the ground over here. That means I let it be 0 here, and I know this is 20. So this is 20 more than the ground level. And also it shows the difference, right? The comparison, the change. How much change is this point relative to this point? Compared to this point, how much is the change? How much is it more than this one? That is all we're interested about. So is it really 20 joule? Is it really 20 joule, the gravitational potential energy of the object? Now, according to the theory of gravitational potential energy, this 20 joule, it is not the actual value. It is not the actual value. In other words, I would say that it is not absolute. Absolute, okay? Not the absolute value. That means you can think of it like actual, not actual value. It is just a value relative to my reference point. Okay, let me give you one example so that you understand this, okay? Now, think of it like we got 3 points, okay? We got point A, and then we got point B, we got point C. I put a ruler here. And then this is, okay, let me fix my ruler. Okay, over here. At 0, 1, 2, 3, 4, 5, 6, 7, and 8. Okay, I got 3 points that I measure with a ruler like this. Now, where is the actual 0? Let's say I put a ruler here just for you to see the scale. So the actual 0 is at point A, correct? This is reference number 1. Actual 0. The real 0, okay, the true 0. Now, there are 2 ways I can take measurement of C. If I want to find C, I can just say C is 8 units from A, right? C is 8 units, which is also the true distance because your true 0 is at A. So your C is 8 units, that is a true distance. So I would say that 8 units is the absolute. Okay, the absolute. Now, I can also change my reference point. Let's say I want to measure reference point number 2. I let this be my reference 0 here. But in the actual case, is it 0? No, right? It's 4, right? It's 4. The absolute value is 4. But I let it be my 0. And then I make measurement of C with respect to my reference 2. Okay? So how much I'm going to say, what is the magnitude? Okay, 1, 2, 3, 4 units. So I would say that 4C is 4 units. What is this? 4 units, is it the actual value? It's not the actual value, right? It is a relative. Relative to what? Relative to my reference point. I use my reference point number 2 to make the measurement. Okay, so I would say that C is 4 units. This, the second case, this is same as your PE equals to mgh. Meaning that for all the calculations of mgh, we are taking the potential energy relative to the ground, to the reference point. You can think of it like point A is our center of the Earth. This is the center of Earth. Point B is like the ground. And point C is our mass M, our object. Okay, this one, 20 joule over here, it's from the ground. So any measurement I make is relative to the ground. Is it the actual value? It is not the actual value. So PE equals to mgh does not measure the absolute, not absolute. It is a relative value. Why we want to do that? Why want to make things very complicated? Why want to do that? Just take the 0 at the center or at infinity. Because in most of the measurement, we do it at the surface of the Earth, where the G does not change, right? In gravitation, you have learned about the gravitational field strength. It will change with altitude. But in most of the measurements that we do is at the surface of the Earth, right? So it makes sense to just use 0 at the ground, and it makes all the calculation become easy. Okay, because if all the calculation is going to do at the surface of the Earth, then why do I take the 0 point at infinity? That just make things very difficult, very hard. Okay, so I just changed my reference point to the ground, and all measurements is relative to the ground. Okay, so but just to let you know that in the actual case, gravitational potential energy is not 0 at the ground, because you dig a hole, it's still 4, right? So it is at 0 when it is at the center, and at infinity when there's no more gravitational field, no more gravitational acceleration, attraction. Okay. So just to sum up a little bit for this one, we can say that PE equals mgh. This one we use for small scale. Okay, and where's our reference? Ground level is our reference axis, that is our 0. And it is used to measure relative magnitude. Okay, used to measure the relative magnitude. And you only use this when it is small scale, like the first a few 100 kilometers, right? Vertical up, where the G still is the same, still is constant. Okay, there's no significant effect on the of the G. So we can use this one. Now, for bigger scale, for astronomical scale, we cannot use this one because the G no longer the same. And also the reference point we have to change, because if we are dealing with planets, satellites, okay, all this stuff in the space, then we would use the reference point at infinity, which is the true reference point, the true 0 at infinity. Okay, now you see, let me get some space here. I'm going to erase this down here. Okay. For large scale, what happened to the G? G varies, right? G varies. So from Newton's law of gravitation, we have two masses. Again, recall a bit, separated by the distance measured from the center. We can derive gravity is gmm m1 m2 over r square. Okay. Now, if I want to find the strength of mass number 2, the gravitational strength of m2, then I would divide this by m1. Divide by m1, divide by m1. I can cross like this. Okay. So that means this one become my G, the field strength of mass 2. So gm2 over r squared. Like this. Okay. So this is the field strength of mass number 2. Now, from the PE equals to mgh, let's say I want to calculate the gravitational potential energy of mass 1. Mass 1 could be any object on planet 2, okay, separated by a distance. Right, so the PE of m1 is equals to mgh. So I derive a little bit from here. This is m1 gh, right? m1 gh, and I substitute this g inside here. So I get m1 gm square over r square. And I have h. H is just r, height. All right, how high is it placed? Measured from the center. So r. This one go in, this one cross. So we get g m1 m2 over r. That is my P, and we don't write P here. Usually you'll see they write U, G. The gravitational potential energy is equals to G m1 m2 r. Here is my formula for the gravitational potential energy that we use when we want to calculate bodies in outer space, in astronomical scales. We no longer use this one here. This one, usually you'll see there's a sign. There's a negative sign in front. Why there's a negative sign? This makes things very confusing. Why there's a negative sign in front? Okay, let me explain. You see. Okay, let me clear this first. Very quickly, you take a screenshot if you want to take. And I clear this, I get some space here. Continue from here. Now, we have UG, GM1, M2 over R, right? This is our gravitational potential energy. Okay, recall two things. Number one, gravitational potential energy increases with altitude, correct? The higher it goes, it increases. Number two, gravitational potential energy is 0 at 2 points, center of the Earth and also infinity. Here I would write infinity because there's no more field. At that point, at infinity, body just floats, do nothing, right? No more field, right? These two things, we have to make sure that our equation satisfy these two. You see, there's a problem with our equation here. If I increase the distance, if R increase, okay, let me draw this. Let's say this is the Earth. And I go higher in altitude, the potential energy increases, correct? Okay. And if I go further enough, very far enough until infinity, you can think of it like I'm at the edge of the gravitational field. This one, the EP is 0. So if I increase altitude based on my equation, this one, if R increase, what happened to my potential energy? Decrease, right? As this value R gets greater, this value comes down, decrease. But here it says that the EP should increase with altitude, right? But how come this one is decreasing? EP should increase with altitude, the first one. So I have to make an adjustment, right? I have to make a little bit of adjustment that I'm going to add a negative in front so that it makes more sense. You see, when I increase the distance, when I increase R, what happened to the value of the UG? It approaches 0, right? It gets less and less negative. If I increase the value of R, this whole fraction gets less and less negative. In other words, they approaches 0. Eventually, they are going to be 0, hit 0, if I keep on increasing the R. Okay, so it approach 0. Now, if you think of it from the mathematical standpoint, this one is a scalar unit, right? It's a scalar. Energy, right? Energy is a scalar. So scalar, negative sign, mathematically means that it is increasing. If you go from -10, -9, -5, -2, -1, and to 0. When you go less and less negative, mathematically, you are increasing in the magnitude. Okay, so the negative here does not mean the direction because this is a scalar quantity. So this, by adding just one sign, negative, then it matches everything. Here, it matched point number 1. EP increase with altitude. So if I increase the R, that is actually increasing. But the increase is as in getting less and less negative. Is getting less and less negative. That is also increasing. Doesn't have to be like positive. I can go -100 to 0. I'm adding 100. I'm increasing 100 here. Okay, normally it's 0 to 100. That's plus 100 also. I can go from negative, I can go from more negative to less negative. Okay, now it fulfills my first point, and also it fulfills my second point, which is my EP at 0 at infinity. So as I increase this R large enough, then at some point at outside here, it will reach 0. So you have -10, -9, -5, -1, and 0. Okay, so this is the reason why we add a negative in front here. So I can write my general equation of the gravitational potential energy as UG equals to minus GMM over R. And this becomes my GPE, like this. Okay, now recap a bit. This one we use to find, is used to find absolute value. Why? Because where is our reference point? Our reference point is at infinity, which is the true 0. There's 0 potential over here. The ground still has potential, but at infinity, there's 0 potential. So we are comparing with respect to the infinity point. That is the true 0. So that is why it gives us our absolute value. Remember our ruler, your point C is 8 units. That is the actual measurement, right? 8 units. Point C, 8 units from A. So this is the absolute value. This gives our absolute value of the gravitational potential. And besides, also here, we want to be able to define what is gravitational potential energy. And here, to define it, we would define it as such, like this. Here is the Earth. Infinity point over here. If I place the object over here at the edge of the field, still there is an attraction. Okay, so meaning that the object will move. The object will move from this point, u infinity, to somewhere here. Let's just pick a random point, okay, UA. Right? Now, I put it here. I do not touch it. I just place it there. What do you think will happen to the object? Move towards the Earth, right? Because it's still under the effect of gravitational. Okay, still under the effect. So meaning that it will move towards it. That is the natural motion, correct? Natural motion. All right. What happened when object move in natural motion? What happened to the potential energy? The potential energy decreases. Okay, decreases. And this makes sense because over here is 0. What is the over here? Is minus gm1 m2 over r. It's getting negative, so it decreases. It's going down to negative. That also means any point inside the field has negative gravitational potential energy. Any point inside the field is negative gravitational potential energy. Okay, so if you have a graph of potential energy, then you'll see that all the values are in the negative. Okay, they are in the negative because my 0 point is outside over here. Okay, so now when I place the object over here, it moves here. Who is doing the work? Am I doing the work? I'm not doing the work. I just place it there, right? Let it move. So the object itself is doing the work. Or you can say the Earth is doing the work on the object. Okay, same thing. I'll just say, okay, the object is doing the work by itself. So the object by itself, it moves over here. The gravitational potential energy decreases, and I can calculate the gravitational potential energy at this point by using this formula here, correct? So I would define it as gravitational potential energy is the work done to move an object from infinity to that point. Okay, you can say gravitational potential energy at a point. Gravitational potential energy at a point is the work done to move an object from infinity to that point, like this. The object, work done, move from here to here. So gravitational energy is given by minus gmm over r. Is same as the work done, right? Because work done is the change in energy. Here, it has done work because you got force, you got displacement. So work is done. The magnitude of the work done is the same as the decrease in the gravitational potential energy. So I can define it as GPE at a point is the work done to move an object from infinity to that point. Please remember, do not confuse with gravitational potential. Okay, how do we define gravitational potential? Potential, okay, potential, just what do you expect to get if you place something at that position? It is location based. If you do not place something, there's nothing happen, no outcome, right? So gravitational potential means that you can define it as the work done to move a unit mass, okay, a unit mass from infinity to that point. Again, we say gravitational potential at a point. At a point, okay. Okay, you so per a unit mass, right? A unit mass means our GPE divided by m, right? This is our gravitational potential. Should be, I put UG. UG divided by M, gravitational potential energy. Oh, sorry, gravitational potential. Okay, this is gravitational potential. This is gravitational potential energy. Okay, I'm going to show a few examples. Okay, you can take down this one and we'll go to the examples. Okay. Okay, let's say we have a planet with the mass m1, assuming that all the mass is from the center, right? So it has a radius r, and here we draw a line. This is the gravitational field. Okay, take 2 points. Let's say we have point A, point B. Suppose that there is a spacecraft travel. Okay, initially it is at point A. Our spacecraft is at A, having a mass m2. And the distance from the surface is r, and the distance of point B from the surface of the Earth, of the planet, is 2r. Find the change. Okay, let's say the question asks you, right? Find the change in the gravitational potential energy. So find the change in EP. Change in gravitational potential energy. So you use the derivation. So this is algebra, right? No values given, no values given, but we do know a few things. At infinity, what happened to the EP? 0. And going to infinity, what happened to the EP? Increasing. Okay, we do know this thing. That means the potential energy at B is greater than potential energy at A, right? Because we're going from A to B increasing. We want to calculate what is the change from A to B when the spacecraft go from A to B. So here I would use U, okay, gravitational potential energy at point A minus GMM over R, right? But what is the R? R is measured from the center of the planet. So here it has a radius R plus the altitude R. So we might write this as GM1, M2 over 2R. Okay. Now for UB minus GM1, M2 over, okay, this is 2R plus the radius, that's 3R. Okay, which one is bigger? UB is bigger than UA. So since we are calculating the change, right, doesn't matter this which one comes first. I always take the bigger minus the smaller, so I don't have to deal with the sign. I know the UB is bigger, so I just take, okay, the change in EP, I would take UB minus UA. So minus gm1 m2 minus, you have another minus, gm1 m2 over 2r. Okay, so this one cancel, cancel, become plus. So you have, we continue here, equals to, this one, I change the denominator. So minus 2gmm 6r plus 3gm1 m2 6r. Okay, so times 2 times 2 times 3 times 3. Okay, so minus 2 plus 3, that's 1 gmm over 6r. So this is my change in the potential energy. That's my answer. Okay, B. Let's say given the speed of the spacecraft at point A, okay, so VA, 7,600 meter per second. And given the mass of the planet, 6.39, power of 23 kg, and also the radius. Meter. And we want to find the V at B. What is the V at B? When it reaches B, what is the V? So again, we use the energy theorem, right? So we know that when you go from A to B, there's a change in potential. Now the change is increase or decrease? You have to know increase, right? Increase, because I know going higher, potential energy increase, right? So it's getting less and less negative. Increase, that means something has to decrease. Something has to decrease. What is it? The kinetic energy has to decrease. Conservation of energy. Now, but here I'm going to make an assumption. What is my assumption? My assumption is that no other influence of gravitational field by other planets. The interaction is only between this spacecraft and my planet, this one. No other influence. And second thing I'm going to assume is that the spacecraft is already outside the atmosphere. It's already outside the atmosphere because we don't want any resistance, right? Because resistance, it causes energy loss. So this is the atmosphere, the spacecraft already outside. And also there's no resistance, okay? No resistance due to air. So I can say my change in potential is equals to the change in my kinetic energy, EK, like this. Okay, so how do you find the final speed? Just sub in the values, okay? Just sub in the values. So we have, right, so let me put it like this, half m square, half mv square, right? Our kinetic energy formula. So be careful, the m, don't put the wrong m. This m is the spacecraft, the spacecraft m, not the planet. So half m2, I write m2 here. m2, and which speed is greater? Is it at A or is it at B? VA and VB. Which speed is greater? VA would be greater than VB. VA greater than VB. Why? Because if the gravitational potential energy increase, kinetic energy decrease, right? So kinetic energy decrease, that means the velocity at B is smaller than the velocity at A. So VA bigger than VB. So I would take this one half m square. I would take the bigger one, VA square minus m square VB square equals to my GMM over 6R. Okay, so take out this one, m square VA square minus VB square. GM1, M2, R cross, move the 2 over there, I get VA square GM1 over 3R. Okay, so my equation becomes this one. Then I just sub the value in 6600 square minus VB square equals to times mass also given. Okay. And we calculate what is VB. (7320) meter per second. Okay, so velocity at B 7320, velocity at A 7600. Velocity decreases. And this also makes sense because from our previous lesson, remember the satellite? The higher it goes, what happened to the velocity? The smaller the velocity when you're further away. The smaller the velocity if you want to maintain this circular motion. If you're closer to the planet, if you want to maintain the circular motion, you need to move faster. Okay, you need to move faster simply because the force of attraction is stronger. If you do not increase your speed, then it will attract you towards the center of the Earth. Okay, example 2. Let's say we have a satellite moving in orbit number 1, the outer one. And then let's say it run into some resistance, some air resistance, and it falls down to lower orbit. Lower orbit, so now it is in orbit number 2 over here. Okay, the radius given, the outer orbit is 7.34 times 10 power 6, and the lower orbit is 7.30 times 10 power 6. What is the change in the gravitational potential energy? Again, we want to find what is the change in EP. Okay, you want to write U also can. Change in gravitational potential. Okay, is it increase or is it decrease? Now, when it lowers the altitude, then that means it is getting closer, right? Closer to the center of the Earth. So that means the gravitational potential energy, what? Decrease, right? Decrease. The gravitational potential energy decrease. Now you know it's decrease. So if gravitational potential decrease, then something has to increase. The kinetic energy increase. So you can kind of already expect that the speed here is larger than the speed here. Okay, the speed at lower orbit is larger than the speed at higher orbit. So we want to calculate change in potential energy. Same, we find change in potential energy equals to, which one is larger? Okay, let's put some point in. Let's say this is point A. This is point B. Point A is further away, higher altitude, so it's larger than point B. Yeah? So we take UA minus UB. Okay, bigger minus smaller, then I take equals to US minus GM1, M2 over radius, okay, the radius A, minus GM1, M2 over RB. Okay, so now again, not all the values given here. So let's say we use gravitational constant and the mass of the planet, M, as 4 times 10 to the power of 14 kg. And the mass of the satellite, 620 kg. Okay, this is actually one of the questions from the past year. All right, then we put in the calculate negative 6.67 times 10 times, sorry, 4 times 10 power of 14 over plus 4 times 10 power of 14 over 7.30 times 10, 6. Okay, we get 1.85 times 10 to the power of 8 joule. What is this? This is change in potential energy. So the decrease is decrease in potential energy. So using the conservation, if decrease this much, then kinetic energy has to increase this much if there's no loss. Okay, now you have to be careful. Some questions, they will ask you to calculate the loss of energy here. So you couldn't just, every question, I assume this one equal to this one. No, okay, depends on the question, depending on the question. Okay, guys, I'm going to give you a 5-minute break. What time is it? 8:11. Okay, I'm going to give you a 5-minute break. So 8:15 we'll come back. Okay, 8:15 we'll come back. Okay, guys, now I'll continue a little bit more on the escape velocity just to cover up the last part, okay, which is related to this one over here. We go to okay. Escape velocity. Now, if I launch an object from the Earth vertically up, the moment I launched it, there is a gravitational acceleration downward. That means the object is slowing down every second. So if I give it a velocity of u, and then there's acceleration downward, at some point that the velocity v would be 0. Okay, so at 0, then that is the turning point and it will fall back down because it is still inside the field. It is still experiencing the gravitational pull. So the moment it hits 0, it reverses. Now, let's say I launch it the second time. I want to throw this object so that it can leave the Earth. Okay, so I launch it the second time. Now I give it a larger velocity, u. Again, I give it, let's say I give it 1,000 meters per second, vertically up. Now, what is the gravitational acceleration? Okay, we'll just take 10 ms minus 2. Every second minus 10. So how many seconds? Up after about 100 seconds. You divide this one after about 100 seconds, then the v here would be 0 again, right? But here, from this distance to this distance, it is still very close to the surface of the Earth. So here, the g remain as 10. So again, when the final velocity hits 0, there's still g, so it will fall down. Okay, fall back down. Now I launched it the third time. This time I launch it high enough that we start to see that the g changes a bit. So g over here, say 9.8, and g over here, they keep on decreasing. Okay, as it increases in height, the g decrease. And at here, at the tip, g equals to, let's say, equals to 3. Okay, 3 gravitational acceleration now drops to 3 meters per second square, and the object hit 0 at this point. What happened to the object? Still it falls down, right? Still it falls down, even though the g already very small, but it still falls down because you don't have no more thrust here, and it will be attracted back towards the Earth. Now, 1, 2, 3. I launched it the fourth time. This time, I increase, I give it a very large u until the g become 0. Okay, g equals to 9.8, g equals to 5, g equals to 3, and up here, just as this at this point, at this exact point, the g hit 0. And when the g hits 0, the velocity also hits 0. Okay, so that means 0 acceleration, 0 velocity. What happened to the object here? The object, will it fall back down? No, right? Because the g already 0, there's no more force, right? There's no more attraction force. So the object will not fall. It will not fall, and also it will not leave. It will stay here because you got no more velocity. Okay, you got no more velocity. So it just floats in this region of space here at this point. Okay, now this u that I give it, what is this u? You see, this u is the u given to the object at which it does not fall back down. This object does not fall back down. This velocity, we call it as escape velocity. Okay, it is known as escape velocity. Whatever is the velocity that you give it, that velocity is the escape velocity. So in other words, escape velocity is velocity at which the object does not fall back down. Okay, after you've given it, it does not fall back down. It just remains here. Now, let me take it further. You see, let's say one more time, the final one more time I launched it. Now I give it much larger than U. Let's say this is U4. I give it U5, and U5 is much larger than U4. What happened to the object? Again, the G decrease. At some point, the G equals to 0, right? But at this point, it still has got V. It's still moving. Okay, it's still moving. So what happened is that over here, from here to here, you have what we call like a leftover velocity, leftover V. Okay, so you need the V to drive you to the point where the G equals to 0. And then you have extra, that's leftover velocity. So what happened to this extra velocity? This extra velocity is going to propel the object continue moving forward. Okay, continue moving outward. Okay, so we got two velocity here. We got U4, we got U5, right? So let's say U4 is 3,000 meters per second, and U5 is 4,000 meters per second. This velocity, I give it, it can leave the Earth, correct? With extra velocity. This velocity, I give it, it is just enough to escape the gravitational field. Now, here's the question. Which one is escape velocity? Which one is escape velocity? Both also leave the Earth, right? Now, understand, escape velocity is the velocity that is just enough to keep the object from falling. So that means U4 is the escape velocity. Okay? So U5 is greater. So, but we don't say, okay, escape velocity is 4,000. No, it is the 3,000. That is the escape velocity. Okay, so when you want to launch object that leaves the Earth completely in a rocket launch, okay, in space program, space launch, you have to achieve this escape velocity to escape completely the gravitational pull from the Earth. And we can actually calculate this escape velocity. How do you calculate? That's why we learn the gravitational potential. We are going to use the energy for us to calculate this escape velocity. Now, very simple, you see. We know that when we launch something, what happened to the KE? KE is maximum at the bottom. KE is 0 at the top. Okay, so whatever the velocity I give it, let's say this is the escape velocity U4 that I give it, I'm going to call this VE, escape velocity, okay? Now, so the KE loss is equals to half mVE squared from here to here. This is for the kinetic energy. For the potential energy, now, particle moving up, object moving up, what happened to the potential energy? PE up here, when it leaves the gravitational field, what is the PE here? 0, right? This is like your point of infinity. This is like your point of infinity. Okay, so P is 0 here. How about the PE here at the ground? At the ground is negative Gm, I would call this ME, M Earth, over R, like this. Okay, so at the ground, your PE is negative. This one is a negative value. But when you go up there, that's infinity point, that's 0. And PE gain, because you're going from negative to 0, you are gaining PE. So how much is the PE gain? Here, 0, larger, we take larger minus smaller. So 0 minus GME M over R. So you can see that the minus cancel out, right? Cancel out. So we only have GME over R, like this. This is PE gain, and this is KE loss. I equate them, half MVE square equals to GME M over R. KE loss equals to PE gain. Cross, then we have arranged this one. We have VE equals to square root of 2 GME over R. This is my equation to calculate escape velocity. What is the G? Constant. This is a constant. This is the mass of the planet. If this is the Earth, then you take the mass of the Earth. If it's other planet, you can calculate the escape velocity of other planet taking the mass. So I just make it general. So I erase this M and the radius of whatever planet that you are calculating. Okay, so let's say I want to calculate the escape velocity of the Earth, right? So you can see escape velocity depends on the mass and the radius. The bigger the planet, the higher the escape velocity, the harder you want to leave the planet. Okay, now here for the Earth, for the Earth, VE equals to square root of 2 times 6.67 times 10 minus 11 times, what is the mass of the Earth? You take the mass of the Earth, and I forgot mass of the Earth. What is it? I think it's 6 point something times 6. Okay, let's just say 6.25 times 10 to the power 24 over the radius of the Earth. 6 times 10 to the power 6. Oh, I see. This is 5.97. Yeah. Mass of the Earth is about 5.97 times 10 to the power 24 kg. Okay. Calculate this, then you can find it's roughly about 11.2 kilometer per second. To escape the Earth, you need to be traveling at 11.2 kilometer in 1 second. Okay, to overcome the pull of the gravity.